Assalamu alaikum. So lecture number 15, and today we'll be talking about antennas and propagation. So here we have the main bullets which we will be going through one by one. First of all, we will be talking about the electric and magnetic field coupling, because whenever we talk about the electric field, so a static charge actually creates electric field around its surrounding, and then when that static charge moves from one point to another point, so the electric and magnetic field coupling occurs. Then how electromagnetic radiations are being traveling when we have antenna radiations. And there are a few concepts which we will be using, for example, period, frequency and wavelength, and then phase lag and phase lead, because if we have current and voltage, so there is some phase lag and phase lead. So why we need antennas? And we have one example analogy from the real life. Then because we sometimes use one antenna for transmission and another antenna for reception. So why we need two antennas for transmission and reception respectively, though we have the option where we can have a transceiver which is actually performing both the transmission and reception functionalities. Then we can also convert a transmission line into an antenna, and how, so we will be talking about this. And after that we will be discussing about the functionality of antenna. There are far and near fields that are very relevant to the antenna, and then antenna characteristics, and these characteristics will include polarization, and there is a relationship between the antenna size and the wavelength, and we will be talking about antenna gain and antenna length. So let's start. If we have an electric charge, so let me draw. So for example, I have an electric charge here. So the electric lines of force will be directed outside. So there are a few properties. These lines of force, they will not be intersecting each other, so we have different electric lines of force. So actually they are originating from the positive charge. So let me draw the negative charge on the left hand side of your screen. So the direction of those, they will be actually towards the negative charge. So that's the electric field around an electric charge when it is static, right? So here we have the situation when we have a positive and negative charge, then they are forced to be placed like this, plus charge and negative charge. So you can see that the electric lines of force, they are actually originating from positive and they are terminating at the negative, right? And you can also note that they are not crossing each other. So whenever the charge moves, so there is an electric magnetic field as a result of charge movement. So in that case the electric and the magnetic field, they are coupled, and you can see here in this figure we have magnetic field, right? And here we have the electric field. So this shows that they are perpendicular to each other, right? And here we have another scenario where you can see the coupling of electric and magnetic field. So at each point of intersection, you can see that the electric and magnetic field, they actually are perpendicular to each other, or you can say they are making an angle of 90 with each other. So here we have a wire, so a charge is moving, so as a result of the movement of charge, you can say current is flowing in the from the conductor. So this is the direction of the electric field, and here we have the magnetic field that is surrounding this cable. So here we have explained the coupling of electric and magnetic field. So those coupling, or those the relationship of the electric and magnetic field, they can be explained by using the Maxwell equations, right? So as mentioned, a moving electric field creates a magnetic field, and that is denoted by capital H, and a moving magnetic field creates an electric field. So they are actually coupled. So here we have another figure where the electromagnetic wave is moving, and you can see different fields in different colors. Magnetic field is represented by this color, and then we have another color for the electric field. And there is you can also calculate the wavelength, because these are the waves in case of their traveling, and they are traveling with certain velocity, so we can have the wavelength. They are the closed loop surrounding the currents that produce them. So they are the closed loop. So here you can see this is also a closed loop, and magnetic field is also a closed loop. So as a result, we can say that we have the electromagnetic radiations. So they are caused by charged particles that are accelerated, that are moving with some velocity. So those charged particles, they have the electric field if they are static, so they produce electric field in their surroundings, but the moving charged particles create a magnetic field, which in turn creates electromagnetic radiations. So sometimes we name it electromagnetic wave, or maybe in some other literature you can see the electromagnetic fields. So here we have to repeat some of the concepts which we already know: period, frequency, and wavelength. So if we look at this wave, so this is a conventional sinusoid wave. So here we have the timer, here we have the voltage. So you can see that this has a time period of 2 seconds, and then we can also calculate the frequency, and because if this wave is traveling with the speed of light, then we can also have the relationship that is S is equal to Vt. So here we have mentioned C is equal to lambda into F, right? So it's the same relationship, S is equal to Vt. So if we want to calculate the T, so time period is 2 seconds, so the reciprocal of time period is frequency, so that is 1 by 2, this is equal to 0.5 Hertz, and then we have lambda, because C we already know, 3 into 10 raised power 8 meter per second, so we have to put all the values so we can calculate the value of lambda. We know the frequency, we know the velocity, and by putting the values we can calculate the lambda. So this is also important because when we talk about the electric field and magnetic field, so maybe they have some delay, right? So maybe if I go back, so here you can see that we have two waves, one is representing electric field and the other one is representing magnetic field, so they can lead and lag. So that's why we need this concept, relative timing of two signals. So here we have two signals if we are talking about the electric and magnetic field. So we can calculate the absolute time in seconds, and here you can see that phase lag, we will be showing phase lag. So signal 2 lags signal 1 by 45 degrees. So here you can see that this is the lag. So here we have 0 and this is the lag, right? So this amount is the lagging and this is actually 45 degree or pi by 4. And then phase lead. So here you can see signal 2 is leading by this much amount, that is again 45 degree pi by 4. So here the signal that is represented by this plus symbols is leading the solid line signal by 45 degree. So after knowing the coupling of electric and magnetic field and how the electric and magnetic field can be traveling along each other, and knowing the period, frequency and phase lag and phase loop, now let's come to the antenna. So first of all we have to go through the normal or conventional communication system. So we have a transmitter and a receiver, right? And in between we have the communication channel or medium. So this can be free space for radio waves. If we have the wired media or guided media, so we can have maybe UTP or maybe fiber optics, and there can be other medias also. So alongside this medium we have the noise, right? So our objective is actually to transmit the data from here. It can be a data, audio, video, and maybe the data from the computer, and then this data has to be sent over here. So in between we have the channel, and that channel is actually noisy. So noise is omnipresent, so it has to be there, and this is impossible that we can escape noise. So the first object that we are facing when we talk about the receiver, right? So at the receiver we have to receive the data in the form of signals, right? And those signals are being transmitted by using one of the medium, free space, wire, fiber optics, and cable. So if we talk about the free space, then and we are at the receiver side, the first thing that will come in our way is the antenna, right? And whenever we have to transmit the signal, so the last entity that will be transmitting the signal into the free space is actually the antenna. So here we have the example, or you can say the analogy regarding antennas. So first we need to understand the functionality of the communication system. So on one side we will be sending the data, and on the other side, that is the receiving side, we will be receiving the data. So in between we have the channel, and that channel is noisy, and we have to receive the or retrieve the data so that the actual data is received in an effective and efficient way. So let's talk about the human ears, right? So they work like antennas. So the human ears, they have the capability to capture the vibrations between 20 Hertz and 20,000 Hertz, right? So when I'm talking, so it means my voice is lying between this frequency range, then the human ears, they are capable of receiving my voice. So let's talk about the actual data plus noise. So if I'm talking and somebody outside is also making some noise, so in that case you cannot stop your ear in order to receive that voice, right? But your brain, which you can say is the processor which is processing this those signals that are being received, so it will only focus on the voice that is actually the lecture or my voice, you can say, right? So this is the perfect example. So if I consider one ear, right? So you can see that one ear, if I block or maybe put some object so that my second ear cannot receive the voice, right? So then my capability will be reduced a bit, right? So you can say that both the ears, they are actually acting as an array of antenna, and the sound as a result is magnified in our processor, that is the brain. It can magnify by receiving both signals from two ears, and then we can hear or we can understand in an effective and efficient way. But there is one problem when we take the example or analogy of regarding the receiving antenna, and we take a human ear at the receiving antenna. So our voice, it gets lost when it has to traverse a distance, right? So there can be a lot of reasons. There can be some obstacles, there can be some walls, or maybe distance, right? So we need, if we want to communicate our voice at a distance, so we need to do something else, right? So in order to increase the distance, what we need to do, we need to use radios, and radios, they actually are relying on antennas. So let's talk about the history of antennas. The antennas were first used by German physicist Hertz in 1888. So actually he was trying to verify or prove the equations proposed by Maxwell. Most of the electromagnetic theory and transmission line and other subjects that are relevant to the EM theory and EM waves, they are based on the Maxwell proposition. So he was trying some experiments in order to verify or justify the theory proposed by Maxwell. And what he was doing, he was using dipole antennas at the focal point of parabolic reflectors for both for transmission and reception. So he, on the basis of this experimentation, he published his work in one of the physics journal. So here we have the definition, you can say, of an antenna. An antenna is actually an electrical device which convert electrical current into radio waves and vice versa. So when we talk about the transmission antenna, so it actually is transmitting the electrical currents into radio waves, and when we talk about the receiving antenna, so it is actually receiving those radio waves, and there is some circuitry or termination point where those waves are received maximally, and we convert those waves into electrical currents or whatsoever is required. So in transmission, a radio transmitter applies an oscillating radio frequency electric current to the antenna's terminal, and the antenna radiates the energy from the current as electromagnetic waves. So this is the transmission. And on the other side, if we talk about the receiving antenna, so we try to receive maximum energy that is being received and try to convert that energy into the electrical. So we have two different types as mentioned: transmission antenna, any structure designed to efficiently radiate electromagnetic radiation in a preferred direction, right? So we can also have the directional antenna, or we can also have the omnidirectional antenna. So there are a lot of different types of antennas which we will be discussing at a later stage. And in case of reception, an antenna intercepts some of the power of an electromagnetic wave. So it's not possible to receive all the power, so we try to receive the maximum power that is present in an electromagnetic wave. So the objective is to convert that power into the voltage at its terminal that is applied to the receiver, and then we have the amplification in order to, because the signals become weaker, so we amplify. So we can also have a transceiver that is performing the functionality of both the transmission and reception. So here we can have one question that why we need to have separate transmission and receiving antenna. So there are a few reasons, and they actually are relying on the requirements. So transmission antennas need to deliver strongest possible signal into the target area compared to the other antenna. So whenever we talk about the transmission, so our objective is to transmit maximum possible energy into the atmosphere, into the free space, so or whatsoever we actually are using, or maybe water. And here the efficiency and gain are the most important factors, right? But in case of receiving antenna, we need to receive the best signal to noise ratio. So when we talk about the transmission antenna, so we want to transmit the maximum possible signal into the target area, and whenever we talk about the receiving antenna, so we need to have best signal to noise ratio. So here you can see and you can feel the difference, that the gain and the efficiency have to do nothing with the SNR, signal to noise ratio. So let's talk about the basic structure of an antenna. So if I take the antenna as a transducer, so transducer is a device that converts energy from one form to another form. So at the one side of the antenna we have electric currents, voltages, and on the other side we have to convert those voltages and currents into the electric and magnetic fields, or EM waves, right? So in case of the basic structure, it's actually a metallic conductor, and it has the capability of radiating and receiving electromagnetic waves. So antenna can send electromagnetic waves, and it can also receive the EM waves. So typically an antenna consists of an arrangement of metallic conductors, right? So we actually arrange those metallic elements in such a way that they, in case of the transmission antenna, they are radiating maximum power into the surrounding, and in case of the receiving antenna, they try to receive as much power from the EM waves as possible. So normally if we talk about our transmission line, for example, let me draw here that we have a transmission line over here. So there can be different circuitry over here, but what I can do, so let me draw here. So I can cut this transmission line, and then I can leave it open, right? And here we can have the antenna. So this can be an antenna. So here we have the oscillating current, and the electrons are forced through the antenna by transmitter. So it will create an oscillating magnetic field, and that magnetic field will be actually having oscillation as the to and fro motion of electrons here, and then we have the coupling of electric and magnetic field, and as a result the energy is actually radiated into the atmosphere. So this is the basic structure and basic antenna we can have. So let me draw the figure again in order to show this transmission line antennas, because we have the basic structure. So here we have the time varying fields, and those time varying fields radiate in the atmosphere from the antenna into the space. So as we are having a moving electromagnetic wave. So this is the case where we have the transmission. So in case of reception, the oscillating electric and magnetic fields of an incoming radio wave exert force on the electrons in the antenna. So here we have the electrons, so the fields which are present here around those edges, they will exert force in the antenna elements, causing them to move back and forth. So here we have the oscillations, and we have the circuitry maybe over here. So those circuitry is actually amplifying, and here we have the oscillating current, right? So then we can also have the same antenna as transmitting and receiving. So in case of two-way communication, right? So then we have to take care of the antenna reciprocity, because as we move on, when we talk about the transmission point and the reception point, so the fields, they are becoming weaker and weaker, so we have to take care about the antenna reciprocity. So there can be different type of antennas and different characteristics that are being provided when we talk about the antenna structure. So they can also contain reflective and directive elements or surfaces not connected to the transmitter or receiver, such as parasitic elements, parabolic reflectors. So the best example is the dish antenna. So you can see that we have a parabolic surface at the base of that antenna, so that the receiving signal is focused maximally on the focus of this parabola. Then and that actually serve in order to receive the maximum possible signal. Then we can also have different types of antennas. So an antenna can radiate in all directions, that is omnidirectional antenna, or we can also have line of sight communication, where the transmission is being done or performed by focusing on a certain receiving antenna. So here we have to justify that why we need antennas, right? So as mentioned that in one of the example, that if we talk about the human voice, so we have the limitations, right? So we cannot transfer the voice at a longer distance. So that's why we need to convert that voice into electrical signals, and those electrical signals, in some cases we can launch them onto wired media, and in some cases, if it is not possible that we can lay down the wired media, so we use the free space, and as one of the best example is the cellular services that we are using. So whenever we want to make a call, so cellular service is there, so we can transmit our voice by using the communication system, antennas, and all the concepts, and we actually overcome the deficiency, right? So we need antenna when two persons, they want to communicate each other and it's not possible to have the wired communication, right? So antennas are required in order to send and receive data, right? And radio waves are being used, or you can say EM waves, which carry signals by using air, free space, and the velocity of the EM wave is comparable to the velocity of light. So radio transmitters and receivers are used in order to convey signals, and that is carrying the actual information in systems, and those systems, they can be broadcast, audio, television, right? So this is simplex, and then mobile telephones, point-to-point communication, links, telephone data networks, and satellite links. So the radio waves are used directly for measurements in technologies including radars, GPS, and radio astronomy. But in each and every case, the transmitters and receivers that are actually involved in order to transmit that data and reception of the data, they need antennas, right? So though in some cases we cannot see, for example, when we talk about our cellular phone, so we cannot see the antenna nowadays. Before a decade before, the cellular phones, they have the antenna, because that technology was not mature enough. So now you can see the size is reducing and the antennas, they are hidden. So another example is if I have a laptop and I have a Wi-Fi access, so I cannot see the antenna, so it's again hidden. And another example is AM radio. So again, antenna is hidden. So then we can ask ourselves where to use. So actually antennas are used in systems such as radio and television broadcasting, then point-to-point radio communication. So we can also use antennas when we talk about the wireless LANs, wireless communication, Wi-Fi and radar and space exploration, when we talk about the satellite communication. So are most utilized in air or outer space, but can also be operated underwater. We can also use antennas because water is also a medium that can be used to transfer data from one point to another point. So in order to accommodate underwater communication, so we need antenna again. So here we have more explanation in order to convert a transmission line into an antenna. So here you can see that we have a transmitter, and this is the transmission line. And what I did, I cut this transmission line and I expanded or bent at right angles, and they have the same length, right? So here there's some error, so it should be like this. So this is the length of the two bands. So here you can see that the length of this band is lambda by 4, where lambda is the wavelength this transmitter or oscillator is creating. So bending at right angles, it can produce an efficient radiator. So if we talk about the electric and magnetic fields over here, so you can see that this is positive and this is negative. So the fields, they are actually originating from positive and terminating at the negative. And then we can also see the surrounding magnetic field over here, right? So now support each other, right? And we can have the optimum radiation occurs when the length is 1 by 2 of the wavelength, right? So if we have this total length, when we talk about the coupling of electric and magnetic field, is equal to lambda by 2, right? So here how this is happening, right? So for example, an AC current flowing in wire produces an EM wave, and let's assume that IT is the current that is applied at A with length L. EM wave will travel along the wire until it reaches at B. So I'm taking this point A and B, right? And B is point of high impedance, right? So you can see that the high impedance waves reflect back, because normally the waves, they got reflected when they come across the high impedance towards A, and it is reflected back again. So resistance gradually dissipates the energy. So as we know that all the conductors, they offer resistance, so as a result of this resistance, this conductor will dissipate the energy of wave. Wave is reinforced at A, so as a result we have continuous oscillation of energy along the wire and a high voltage at A end of the wire. So there will be a higher voltage, and so the velocity of those moving electrons and moving fields is comparable to the velocity of light. And here we have the length of this wire, and then we have the wavelength, because we have oscillations, so we can calculate the distance between a wave travels during one cycle. So we can also use this formula in order to calculate the frequency. So here we have the dipole antenna, two wires each with length L is equal to lambda by 4 attached ends to terminal of a high frequency AC generator. So here we have the high frequency AC generator, and we have connected those wires to this high frequency AC alternating current generator. A right angle is right side plus, and the left side is negative, right? So you can see on the right side we have a plus, and on the other side we have the negative, because this alternating current, so the polarity is changing with frequency f. So one side is having the length lambda by 4. So electrons flow away from negative because they will be repelled due to polarity, negative polarity, and towards the positive terminal, right? So most current flows in the center and none flows at the ends. So most of the current will be at the center, and there will be no current at the ends. At any point will vary directly with Vt. So you can see that 1/4 cycle, after 1/4 cycle, electrons have begun to flow. Maximum number of electrons will be at A and minimum number at B, right? Because the electrons are being repelled here, and then the electrons here, they will be attracted here. So we have maximum number of electrons here and minimum number of electrons here at B. So V max T is developed, It is equal to 0. So as a result, you can see that we have this sort of scenario where we have the oscillations and the dissipation of energy will take place, and as a result we have the coupling of electric and magnetic field. So there are certain measurements that actually are involved in order to have a good antenna. So one of the factor is either a near field or far field range with appropriate implementation. So there are significant cost, size, and complexity details which will lead to the recommendations, right? So we have to find out that what antenna will suit us. So because we don't want that if our communication system, it can operate by using an antenna that is having low cost, and of course the size is also one of the important factor, and the complications that are being involved when we are talking about the transmission and reception, right? So there are some important factor, and one of the important factor is the near field and the far field. So in general, the far field ranges are better choice for lower frequency when we talk about the transmission and reception and low frequencies, right? So we can choose far field ranges, and where the simple pattern, it can cut the measurements, right? And the near field ranges are better choice for high frequencies when we have to transmit and receive, or we have the data communication and high frequency antennas. Then by using high frequency antennas, then near field ranges are better, right? So antenna with a periodic signal create electromagnetic radiations. So we have two type of electromagnetic radiations, near field and far field. So here we have some of the details regarding the near field, that is actually the inductive coupling. So you can see that we have the inductance, and that is producing inductive couplings in the circuitry at the tag side. So area from the antenna to the point where the electromagnetic field forms, fields start at the antenna as purely magnetic, right? So inductive, so like a transformer, when we talk about a transformer, so you can see that we have secondary and primary coils like this, or we can also have a capacitive coupling. So magnetic field decreases by a factor of 1/r cube in free space. So as we move away from the antenna, so the field power or the radiation power decreases as 1/r cube in free space, where r is the distance between the tag and the radar antenna, right? So you can also have the example of RFIDs. So here enough power of cryptographic function if tagged close to the reader. So here we have a far field. Actually it is also called the radiative coupling. So area is at some distance from the transmitting antenna, at which the electromagnetic waves has fully formed and separated from the antenna. So you can see that there is a separation from antenna, right? So the electric and magnetic fields propagate as the conventional and native EM wave. In the far field, inductive coupling is not possible because they are at a long distance. So for coupling, you need to place them very close to each other, so they are not very close to each other, right? So that's why the inductive coupling is not possible. So here again, as we move away, there is a decrease in the power of the EM wave, so that the EM field decreases by a factor of 1/r. So you can see its reciprocity over here, where r is the distance between tag and the read antenna. So here we have the approximation between near and far field. So in one case, if the antenna size is incomparable to the wavelength, right? So as we know that the EM waves, they are traveling with some frequency, so we can also calculate the wavelength. So like for example UHF, ultra high frequency. So here we have R is equal to 2F d square over C, d maximum antenna dimension, and F is the frequency and C is the speed of light. So in another case, if the antenna size much smaller than the wavelength, like HF, high frequency, so here we have R is equal to C 2 pi F, right? So again, F is the frequency, C is the velocity of light, and we all know the value of pi. So here we have the boundaries for near and far field. So this is the band, distance in meters and distance in feet. So low frequency 382 meter, and it comes out 1146 in feet. High frequency distance is 3.5 meter, and in feet 11. And then ultra high frequency, so you can see the distance 0.16 meter, and in feet we have 0.5. So as mentioned that we can take antenna as a transducer that is actually converting energy from one form to another form. So if we look at our left hand side, so we have a generator, so that is actually generating currents or maybe voltages, and this is an alternating source in case of current or in case of the voltage. So here we have the transmission line, and we have cut down the transmission line and bend it in this way. So you can see that we have the guided EM wave that is traveling along this transmission line as a result, because we have bent their ends in such a way that they are forming actually an antenna. So those ends, they are actually radiating the EM lines in the free space, right? So here we have one form of energy, and here we have converting this energy into another form of energy, that is the EM waves, and they are traveling with some velocity. So here as a result, wave is launched into the free space. So here we have some of the physical characteristics of antenna. So actually the antenna size and the shape, it determines the frequencies it can handle and how it will be radiating the electromagnetic waves into the surroundings. So we can have different antennas of different size and different shapes. So here we have the thin dipole, biconical dipole, and here we have the loop and helical horn antenna, and here we have the microstrip antenna, and this sort of antenna is used in order to provide communication for RFIDs. Then another one of the characteristic of the antenna that is very, very important is the antenna polarization. The polarization of an antenna is actually referred to the orientation of the electric and magnetic field it produces. Right? So it actually determines the orientation of the electric and magnetic field. So here we can have a figure where you can see that the electric and magnetic field, they are polarized, and you can see the direction of propagation, and we can also have an idea about the polarization. So the polarization is much important because the receiving antenna should have or should support the same polarization at the transmitting antenna in order to receive the maximum power, right? So if we have a transmitter and the receiver, so they should have the same polarization configuration so that we can send and receive maximum power. So we have different configuration of polarizations, horizontal polarization, vertical polarization, and circular polarization. So as we know that when the energy is being radiated into the free space or the outer space as a EM wave, so the electric magnetic field, they rotate at certain frequency, right? So the polarization is used when the orientation of the receiving antenna is unknown. Circular polarization, right? So we can also have the right hand circular polarization and then the left hand circular polarization. So these are also some of the, so here if I go back, so you can see that we have the polarization. So this polarization is producing due to the rotation of the electric and magnetic field. So you can see that here we have the electric field in the upward direction, and here we have the direction of the magnetic field. And if I further move here one step back, right, so you can see that the polarization has changed due to the rotation of the electric and magnetic field. Now the electric field is downwards and the magnetic field is on the other side of the loop, right? So this is the, so then we also have a very strong relationship between the wavelength and the antennas. So this determines the dimension of the antenna, right? So the dimension of an antenna are expressed in terms of wavelength. Low frequencies, it means that long wavelength, right? So we need a very large antenna, right? So and high frequencies imply short wavelengths, hence high frequency antennas are usually small. For example, the antennas which are being used within our cellular phone. So we have the relationship, c is the velocity of light, and then we have the frequency of the communication for the communication, and this is the wavelength. So we can calculate the wavelength, so as a result we can calculate the size of the antenna. And here we have mentioned a very basic type of antenna, as we have talked about the wavelength and the antenna, because the dimension of the antenna is dependent upon the wavelength. Wire, a metal rod, or a piece of metal tube. So here we have the best antenna length is equal to lambda by 4 or length is equal to lambda by 2. So this is the dipole antenna. So here we have a basic antenna. Let's start by looking at the radiation pattern of an isotropic antenna. So this is the reference antenna. So here we have the isotropic point source only exists. This is only used for reference, or this is an ideal antenna. An isotropic point source is equally distributed in all directions. That is not the case when we talk about the antennas in realistic life. So it is completely unfocused. So here we have the antenna gain. Again, one of the important characteristic of the antenna, because passive device, so power radiated cannot be greater than the power input power. So we have to pay something. So the input power is greater and the output power is lesser than the input power. Antenna gain is expressed as a ratio of the effective radiated power, output power to the input power. The gain of an antenna, it actually measures the power transmitted relative to that of the transmitted by an isotope. So this is the relative antenna. So we normally compare this to the isotropic antenna. The gain is mentioned in dBs, decibels. So here we have the effective radiated power, or EIRP is the gain of an antenna with respect to an isotropic radiator multiplied by its input power. So here we have the expression or equation ERP, effective radiated power, is equal to input power into antenna gain. So highly directional antenna with a gain of 7 has an input power of 1 kilowatt. Its ERP is therefore 7 kilowatt. So that's it for today's lectures. Today we talked about electric and magnetic field coupling. So how we actually are having the coupling of electric and magnetic field as a result of a moving charge, and then how the EM radiations are produced as a result of those as oscillations. Then there are a few concepts which help us in order to some of the concepts regarding antenna, period, frequency, and wavelength. We also discussed about phase lag and phase lead. Then we talked about why we need antennas. And then we have also discussed one of the real life example, that is the human ear, that is actually acting as an antenna for humans. And we also established that why we need separate transmission and reception antenna, though we nowadays we have devices where we have a single antenna that is acting as a transmitter and transceiver. So we have certain scenarios where we should have transmission and receiving antenna separately. So there are a few advantages, and we have talked about those different advantages. Then we can also convert a transmission line into an antenna. So how we can do that, and after that we discuss the functionality of an antenna, and far fields and near fields, and how they are important for antennas. And then finally we talked about different characteristics of antenna, because they are very important: vertical polarization, vertical, horizontal, circular polarization, and then there is a strong relationship between the antenna size and the wavelength, and then how we can define the antenna gain, and finally we can establish the antenna length accordingly. So that's all. अपना ख्याल रखिएगा. मेरी तरफ से अल्लाह हाफिज़. अस्सलाम वालेकुम.